presence after almost 3 years. I officially opened the 21st International Conference on Image Analysis and Processing. This conference is organized by the Italian Association for Research in Computer Vision, Pattern Recognition and Machine Learning, the CVPR. And this 21st edition, the hosting institution is the Institute of Applied Sciences and Intelligent Systems of the National Research Council of Italy. So I welcome all of you in presence and in remote. Before starting with our first keynote speaker, I would like to invite Mr. Alessandro Delinoci, the Regional Minister for Economic Development, International Policies, Industrial Research, Energy Innovation, and the Youth Policy of the Apulia Regional Government. Please, Mr. Delinoci.
Thanks a lot for the invitation, Professor Distante. Thanks. Good morning to everybody. I'm very glad to be here and have you in my city this edition of the International Conference on Imaging Analysis and Processing. You are here today after quite 2 years without conference and meeting because Lecce is a beautiful location, but above all because Unisolento CNR show determination, capacity, and aimed for excellence in different fields of research. For example, in the artificial intelligence. I remember when, about 10 years ago, as a I remember when, about 10 years ago, as public administrator of the municipality of Lecce, my staff, my colleagues, and I planned and worked hard to make Lecce become a smart city. During that period, one of my interlocutors was Professor Distante, that I want to thank. The IoT, the artificial intelligence, and big data are not the future. They are our present. More and more services that we use and live daily are going in these ways. You know better than me that applications are a universe to discover and that future economy will be based on them. I hope that the future will be the result of your studies and well of your work here in Lecce. Thanks you very much. I hope this is a big opportunity for our city. I hope this meeting will be a success for us and for you. Thank you very much.
Okay, so let's start with our first keynote speaker, Professor Roberto Cipolla from University of Cambridge in UK. Professor Cipolla is well known, so he doesn't need any introduction, but I would like to send my congratulations for his achievement this year. He's been elected a fellow member of the Royal Society. So Professor Cipolla will give a talk entitled Geometry, Uncertainty and Deep Learning, and he will introduce some recent results from real-time deep learning systems that fully exploit geometry, compute model uncertainty, and require very small amounts of labeled data. So please, Roberto.
Okay, good morning. Can you hear me? Okay,
Yes.
Good, thank you. It's very hard to give a remote talk. So good morning. I must apologize for not being there in person, but we've had a number of medical emergencies that keep me here. But I'm delighted and very grateful to Cosimo and Stan, Marco, Federico, and of course, Giovanni for inviting me. So it's going to be an overview of computer vision, maybe just a big picture, start with a bit of history, and some systems which are very efficient with data and how we do that using geometry and uncertainty and deep learning. Now, we're all in this really exciting field of artificial intelligence, and we need to define what intelligence is, and we want to build systems that do the right thing. And I like this definition of intelligence. Intelligence can be viewed as a process that converts unstructured information into useful and actionable knowledge. So it's all about learning representations that can be used for decision-making and action. And our visual systems supply most of that data, most of that unstructured information. As I'm looking now, even at you, gigabytes of data are rushing through the left and right eye, being processed by billions of neurons, consuming, actually, the brain consumes a large amount of our energy. If I think at the moment I'm consuming 100 watts, and my heart, which is beating very fast, is 1 watt, the visual cortex is 20 watts. So a large proportion of our energy footprint goes to powering those billions of neurons. And what do we do with those images? We're extracting representations that allow us to recognize familiar objects and tell us where they are in the scene, to describe the shape of unfamiliar objects. We're learning representations that allow us to move without colliding, to reach out and pick up objects, and to communicate and interact. Those are the core tasks that we want computer vision and our perception systems to cope with. So we all know why computer vision is difficult, but we have made enormous progress. So it's difficult because this is typical of the input to a computer vision system, a video. You might not know this, but I know this is Cambridge. I know particularly which road I'm in, what's happening, what am I looking at, what's going to happen next. But the computer is just given this array, spatial temporal array of numbers, and it's trying to make sense of where am I, where are the objects, what's around me, what is going to happen next. Seems formidable as a task, but we have made enormous progress. So thinking of some of our work here, you know, back in 2009, when we began this work for the automotive industry, we created this database of labeled images, and we used very simple machine learning to try and recognize cars, pedestrians, roads. Zoom forward to 2017, these are real-time systems, very precise pixel classification. We can compute uncertainty, and more recently, we can segment in general, we can segment ignorances, we can even infer distance from a single RGB image. So pretty spectacular progress, I think, and I want to explain some of that. I also should say, even in 2018, these algorithms run real time. They run on mobile phones or embedded processors. You can do semantic segmentation, optic flow, depth, real time on these processors, including mobile phones. And more excitingly, these sort of representations are being used to power the next generation of robotics in terms of learning how to pick up objects, language, communicating, and in our work, learning to drive. So this is an example of one of my PhD students, Alex, and my other postdocs, Jamie Shotton and VJ, who've gone out and built this company, which is learning to drive purely from cameras, not LiDAR, no rules. It's not a hybrid system. It's an end-to-end system from images, 6 cameras, and it's processing those images to recover these representations, mainly on semantic segmentation, optic flow, and depth, which allow it to negotiate very crowded London scenes with traffic lights, pedestrians, cyclists. So these are some of the most challenging situations for autonomous driving, and this is working. They've got cars in London doing this every day. So a really exciting time to be in computer vision, I think. Now, you all know the most exciting applications. Mine, I'm particularly interested in robotics now, but in the past, we've all been interested in things like digitizing the world, cultural heritage, augmented reality, wearables, e-commerce in particular, virtual try-on. But I think the most exciting, most difficult challenge is really translating to robotics. The sort of things we do in perception don't readily translate to robot action, but I'll talk about that later. So these are some of the applications, and I want to just illustrate an application, a very recent application now, because I think for the sort of students in the audience, this is a golden age of computer vision. It's, there's so many, forget about building generally intelligent machines. There are so many small things that can help our society, productivity, with very commercial applications. So this is an application we looked at during COVID, and it was really to try and encourage people to buy shoes online. And the technology being licensed by an Italian company called Trier. So the idea is people don't buy shoes online because they're worried about the fit. And can we use computer vision on the mobile phone in real time? And we developed very simple algorithms that allow you to detect the feet and reconstruct their shape to 3mm accuracy, and then visualize what the shoes would look like on you in terms of augmented reality, and also a machine learning algorithm that suggests what is the appropriate size based on your foot geometry and the shoe geometry. So here's a little video. I should say, while you're bored in the audience, download the app. It's called SnapFeet. Take off your shoes and take off your socks and reconstruct your feet and tell me if it's any good. So this is what it does. The app, it just, you take your phone, you point it at your feet. This is an older version. The app is much nicer. So it calibrates the camera relative to the ground plane. You put your bare foot first with the right and then with the left. It takes 3 to 5 photographs, does a bit of segmentation and some key point detection, and then estimates the scale and the reconstruction. This is an old version that was working on server. On the phone now, it's done live. It's done real time on the mobile device itself. And then once you've got the reconstruction of the foot, you can then render the 3D geometry. So you can do that as well. You can see whether your reconstruction agrees visually with what the foot looks like. And you can do some manual adjustment if it doesn't. And then you can just choose your shoes, and it will recommend which size is appropriate for your foot shape. And then you have your standard augmented reality, very easy to do, to estimate in real time the pose of the feet and render the computer graphics object on top of them. So I think that's a simple idea. So computer vision, we know what it is. It's really exciting, loads of applications. I always tell all my students, the world is your oyster. You should be doing, these are easy things to do. All you need is a mobile phone and a computer. And then we'll see how we get away with the technology with little data. So how do we make machines see? Historically, I'm going to really begin with a history lesson, the 30 years of computer vision that I've been in this subject for 30 years, and the 3 decades expanding my research as well. So these are the 3 decades, the old man, the middle-aged man, and the young man. I'm the old man now, as you can see. I haven't got the hair. Then you can see that the old man is geometry, the middle-aged man is tracking and registration, and the young person is deep learning. So I'm going to illustrate how we make machines see with the 3 fundamental approaches. Now these aren't set in stone, but these are a simple way of thinking about it. Historically, we began with mathematics. It was purely geometry, no data, no models. It was purely modeling geometry and recovering geometry from images. I'm going to illustrate that with an example of reconstruction. The next decade was all about tracking and overcoming ambiguities in 2D. And it's all about having models, and these models, in particular prime models, are built with data. So it's all about statistical models using data to regularize the reconstruction process. And then the third decade is one you're all familiar with. It's been this enormous one with loads of data, loads of labeled data, in particular supervised learning. And the big example there is recognition. So I'm going to introduce some work, historical work, just to explain these fundamental approaches of using geometry, probabilities, and learning to make systems see. So that's the outline of my talk. I've just introduced it. We're going to look at what I call the 3 R's of computer vision. In school, we talk about the 3 R's as being reading, writing, and arithmetic. In computer vision, I've always talked about the 3 R's being reconstruction, registration, and recognition. And then in the second part of the talk, I'm going to look at applications where we use geometry and uncertainty and very little data. So how can we get away with very little data? So if we use geometry properly and we model uncertainty properly, we don't need as much data as people imagine they need with deep learning systems. So these are some special examples. So let's begin with this history lesson of the 3 R's, how we reconstruct from images, how we detect the position of objects or their pose parameters, and how we recognize. And the sort of work I'm going to illustrate it is with reconstruction, very accurate 3-dimensional model using multi-view stereo and multi-view photometric stereo. Registration is all about pose, but I'm going to look really at model parameters, where we build powerful priors models that allow us to infer things like pose and shape. And the recognition example I'll choose is semantic segmentation, before we move on to real applications of computer vision. So let's begin with the simplest one, historically 30 years ago, geometry. And that's, you're all familiar, but it's probably one of the most important things that distinguish us from pattern recognition. We are all about the 3-dimensional world, and the images we get are 2-dimensional projections of this 3-dimensional world. So understanding perspective is obviously very important. Understanding transformations are fundamental, and using geometry to describe shape is really our big goal. I'm going to begin with a very simple cue that I started when I did my PhD. So again, as I said, 30 years ago, I went to a seminar and I was looking at this seminar where they were talking about the bird called a gannet, which flies down, it sees a fish, and it's always a fixed amount of seconds before hitting the surface of the water that it withdraws its wings. Otherwise, the wings will snap off on collision. So they noticed this was a fixed time. It wasn't a certain height. It was independent of terminal velocity, starting point. There was no stereo vision there. The 2 eyes didn't have enough overlap. So it was a monocular cue, and it was producing time to contact. And the researchers proposed that the birds were computing the divergence of the image velocity field. Now, it's optic flow, and divergence is a spatial derivative, so it's very ill-conditioned. So in my research, I looked at it in a slightly different way. And if you remember your mathematics of Green's theorem, if you integrate the normal velocity around a closed contour, that's the same as integrating the divergence of the vector field in the area. So this is a very simple result, that if you look at any target, in particular this car, and you don't know how big it is or how far it is or what the camera is, the focal length of the camera, but if you just measure the apparent area in pixels, pixels squared, and you move and measure the area again, the area divided by the derivative of the area gives you this time to contact. So this is a beautiful result, that it's completely independent of the nuisance parameters of scale, distance, focal length. It gives you the result that you need to control your car, how many seconds before you crash. So this was back in '92, and to make it work, we had to initialize these contours by hand. But as is always the case in computer vision, it typically takes many years, maybe a decade, for these to be made robust enough to go out in the real world. And in '92, when I gave this talk in Genoa at the ECCV, a researcher called Amnon Shashua came up to me and said, "What a fantastic idea! We should be really producing chips that can process this data for robotics." And he went on to found a very important company using this time to contact.
The mobilized system continuously scans the area in front of the vehicle, detecting all types of vehicles in the path, including...
So I should say the key transition from '92 to this 2002 was object detectors. So in '92, we had to initialize everything by hand and track. In 2002, SVMs were around, and you could detect a target such as a pedestrian or a car. And if you can detect the target, you can measure its, in Mobileye's case, they measured the width, not the area, as my case, they measured the width and its derivative. And they compute a number, which is
Motorcycles.
time to contact.
The system calculates the
So I don't know if you can see, there's a little thing here with a number 1.8. That is the seconds, 1.8 seconds before it will crash in the car in front.
relative speed, and in critical situations, issues both a visual and auditory warning of an impending collision with the vehicle ahead.
So that is a really exciting. Amnon is computer vision's first billionaire. So is our most successful, not just academic, but commercial and entrepreneur in computer vision. So amazing guy. And I think the company Mobileye is just about to be re-IPO'd. And I can't remember the value. I would think the value is something like 30 to 50 billion dollars. So, wow. So geometry is going to be important. And in my own work, I looked at transformations, but in particular, how we reconstruct from uncalibrated images. So this is, again, from 2 decades ago, it's really going from uncalibrated photographs to these very precise three-dimensional models. Again, a single view is ambiguous. We have to look at the object from a different view and find point correspondences. So in its simplicity, we find features and their correspondences and triangulate. That's all we're doing. The clever thing about computer vision is we don't need features. We can find these automatically using feature detectors or correspondence. We don't need to know the cameras. We can calibrate the relative motion to an arbitrary scale. So we don't know the baseline or the scale of the reconstruction. It's really a big optimization problem. And this sort of bundle adjustment software is now readily available with fantastic packages. Photogrammetry is really the big success of computer vision of 20 years ago. Now, points are easy to use to calculate motion and to reconstruct. In my own work, I've never been a fan of the world as points, the world as a three-dimensional mesh. I've always been a fan of the world as objects. And for objects, the most important feature is their outline, the separation between them and their background. And most of my work is really using these outlines for reconstruction, but outlines for detection and outlines for recognition. This is for me the most important cue in computer vision. So my early work was all about using these outlines, and the truth is, outlines aren't a viewpoint invariant. They move over curved surfaces, but you can parameterize the family of outlines in the image to recover the visual whole of surface shape. And these were real-time experiments back in 1992. So real-time computer vision was still possible with these very simple things. We introduced something called the B-spline snake to make this happen. And you can very precisely estimate motion. And once you've got camera motion, you can then use the outline to reconstruct approximately, and then you use texture pixel correspondences to do a very precise, dense reconstruction. And this is work we did on these mannequins, very precise models. The sculptor, this is the UK's most famous sculptor called Anthony Gormley. And he's used our computer vision software ever since 2005. Every sculpture he makes starts with a digitization of his body, and then he scales it up, in this case, 25 meters tall and probably over 5 tons of metal. Here's another example. Typically, these are photographs, 20 or so photographs of the naked body in different viewpoints, and he makes these abstract forms. So this is the sort of objects he makes, which all start with computer vision. A nice application. So that's using multi-view geometry. Multi-view geometry is one of the geometric cues. The other geometric cue is a very well-known one, which is shading pattern. So if we fix the camera but move the light source, still assuming a rigid object, the shading pattern tells us a lot about surface normal. And it's very, very precise. It gives you very good surface normals. And if we integrate those surface normals, we can get shape. Now, this has gone a long way from 20 years ago when it was simple Lambertian distant objects. This is now near field and arbitrary reflectances. But the key idea is you illuminate the object from different viewpoints, 1, 2, 3, a minimum of 3 different viewpoints. And the shading pattern gives us the normal, and we can integrate the normal to get shape. In our work back then was, we instead of moving the light source, we multiplexed colored lights. And this allowed us to do real-time deforming objects. So effectively, the color reflected by the normal depends on how close it is pointing towards the red, green, or blue lights. If it's pointing towards the green, it will be green. If it's pointing towards red, it'll be red. If it's pointing towards blue, it's blue. The actual RGB components in real time give us the normal, and then we can integrate the normal. We can integrate the normal to give us pretty accurate shape. So this is a single view. You can see again, pretty amazing bumps in real time of these objects. And we've also built a near field sensor. We call it the 3D flashlight, which is really cheap, very fast. It just needs cheap LEDs, and it illuminates the object in real time, and you get sub-millimeter accuracy. So this is a very cheap, very precise scanner, just using that photometric hue. And obviously the combination of photometric and geometric multiview, so multiview stereo and multiview photometric stereo, is the way to go in this area. So I hope that's the first R, reconstruction. Geometry is really important, and it's really it's not just history. The geometry is one of the most exciting things in modern computer vision with deep learning. So 3D geometry is one of the most important things. The second component of computer vision, the next decade, was all about models and dealing with ambiguity. A single view is ambiguous. You can't go from two-dimensional pixels to their each pixel distance. In practice, you need to regularize it, and we need to find constraints. And this is really the approach that, whereas the previous approach, geometry, made very few assumptions about the world. It was really just using rigidity and triangulating to recover the depth of each pixel. This approach is all about having models and being able to think of computer vision as hallucinated perception. That is, this is really the idea that perception, and it's Helmholtz's definition, perception is our best guess as to what is in the world given our current sensory input and our prior experience. So what we going from two-dimensional images to three-dimensional world is ambiguous. We need models to regularize that process, and we build these strong models, geometric or statistical, which allow us to regularize. So we have we're really just finding the most likely model parameters, the most likely instantiation of the model that explains what we see. So this is really the next decade was all about this Bayesian approach, this statistical approach. What you're seeing here in the video is a three-dimensional model we built. So we registered 2,000 scans of humans, and then we built a PCA model. And all you're seeing is for each image, which is 2D, you're searching through, I think it's about 50 parameters. The most likely, you're optimizing for 50 parameters, which explain the data. Explain the data in this case means explain the outline, but it could be explaining key points and other shading pattern. So this is this model-based approach. And the great thing about this statistical approach is, and we use the language of probability because it's all about ambiguity and uncertainty. The most important thing is it deals with ambiguity. That is, there is no single solution. You're looking at the most likely or the best, or you want to actually encode this ambiguity. And secondly, if you have uncertainty, you can fuse that image data with another image or another sensor, like an inertial sensor or some measurement. And finally, it was really this statistical process that introduced us all to the importance of learning. So this is really the second component. The sort of examples I wanted to show, I don't know if this is the right, I might have just missed the slide. Yeah, I've probably missed the slides, never mind. So these are the sort of things I wanted to show, that you can take these images and you can get the most likely shape parameter. This is fitting an SMPL model, and pose parameter. From a single view, there's ambiguity. Red means very ambiguous, more than 5 centimeter error. But by combining different viewpoints, uncertainty allows us to fuse how to combine them probabilistically to get the most likely mean shape in this different pose. So this is pretty exciting work. This is all the code is all available and it's extremely fast. I'll talk about it later on, but this is the idea of uncertainty, that you can fuse multiple viewpoints. And in all our work, again, I'm a fan of edges and outlines, not using raw pixels. This is all done real time. You're fitting a model, a pose and shape. The only input you're using is canny edges and key points. And this has all been trained completely on synthetic data, so no real data at all. Once you've built this parameterized model or shape model or prior, the actual training of pose and shape is done with synthetic data. We'll come back to that in a second, but this is the importance of uncertainty. Again, each viewpoint you're seeing here, each viewpoint being estimated single frame, but you're fusing the multiple viewpoints on the right to get the most likely shape. And you're able to get shape accuracy of centimeters at the waist. The most difficult one is the waist, but you can get an accuracy of about 2 centimeters done properly. So this is these are quite useful techniques. So in this aspect of statistical modeling, it's all about registration. Registration is one of the nicest problems that's had enormous progress for key points, how to, for example, find correspondences, and particularly using SIFT. And I mentioned this only because SIFT has these lovely components which remind us of the deep learning approach, which is that you have these feature maps, you filter with these convolution masks to find edges at different orientations. You do a lot of histogramming or pooling to get these descriptors, and you have some nonlinearity to normalize to give us these descriptors. So it's got the three components that we know are very important later on when we do deep learning. Now, as I said, images are ambiguous. The first approach was just to use three-dimensional models to do monocular tracking. So you regularized it by a strong three-dimensional model. We then moved to these statistical models, which we learned, these families of templates, which we learned by projecting computer graphics models. This is all learned from synthesized data using curved surfaces, truncated quadrics to represent the hand, and the projection of quadrated quadrics are truncated conics. So this is all very fast, real time to render these shapes. And you're trying to find the most likely template that matches the image. And in this case, the match is done with chamfer matching. So this is very early work in 2006 doing hands. Again, as I said, the most important thing we've been working on is really shape, not pose and shape, but shape. Over a decade ago, we produced these magic mirrors where you just walk up to, in this case, a noisy stereo camera, and it estimates the most likely three-dimensional shape from that stereo pair. Again, you're inferring things you can't see because you've got this strong model. So it isn't about recovering the depth of each pixel, it's recovering the model parameters, much easier problem. And that's what most of vision is. You know what you're looking at, and you're just trying to initialize the position, orientation, and shape parameters. Again, this is on the earliest applications.
Toshiba's sensing technology captures a highly accurate image and fits the clothes to your body.
So these are over a decade old. So I'm a bit embarrassed because now this is easily done. In those days, these were pioneering systems. But now I think you've seen much, much better on your mobile phone. So back in 2008, so over 14 years ago, we set up this company which allowed you to take a picture of yourself, make this avatar, and close the avatar. So you're taking a photograph, you're making the most photorealistic three-dimensional avatar of it. And then on your phone, you can choose the clothes and render those clothes. So 2008, this company was pioneering, I think, maybe too early. The technology wasn't good enough. Now you've seen this is probably one of the most exciting spaces in terms of human faces, three-dimensional faces, and human avatars, going from images to these, and then trying on clothes and trying on shoes. And yeah, this is big commercial e-commerce explosion happening in the next couple of years. Right, another example. I don't know how am I doing for time. And can I pause? Can you all hear me? Am I speaking clearly? No? I guess you can hear me, otherwise you would have complained. So let me carry on. So another example of registration is really audio-visual, both speech and vision together. And probably the big success of 3 decades ago is active appearance models, which are wonderful for tracking. And then we decided to track those appearance models and the voice and learn how to synthesize purely from text. So this is a 25 megabyte model, very lightweight, using these active appearance models. And you type in text and emotion, it synthesizes the voice and the expression.
Everything that I say in this video has never been recorded. It has all been synthesized from input text. To build me, almost 7,000 sentences were captured, mixed between 6 emotions. I can synthesize using any of these emotions. So far, I haven't been expressive. But if I want to, I can become angry. Or I can be afraid. I can be happy too. Or I can sometimes be sad. Lastly, I can talk in a tender way.
So was that interesting? In a sense, this was 2013. Nowadays, you're going to see some amazing products. I like the one from London, Synthesia, or which is definitely, you go purely from text and it synthesizes the 3D face and voice. So enormous exciting commercial applications. Right, so that's history lesson number 2. The third history lesson maybe is less of a history lesson because it's more or less the last decade of machine learning, and in particular, we started with support vector machines and boosting, and moved on to random forests, and we've all converged. This is some of our early work on using boosting to find hands as gesture interface back in 2006. This is Bjorn Stenger's work, PhD work, and commercialization at Toshiba. But now we can do, with deep learning, we can do the sort of things that seem quite hard. Face recognition was what probably the first big success of deep learning, as well as recognizing from a single photograph. Open pose was pretty exciting in terms of real-time applications. And on the right is our own research, which is this real-time part semantic segmentation. So 31 body parts running off a mobile phone. So you're all familiar with this, I'm not going to tell you. But deep learning has been the power horse of this revolution, supervised learning in particular. And we're brilliant at building these networks with millions of parameters that take your image and classify what's in it. That's been the big success. So classification and object detection have been this enormous success. Again, in 2009, we were approached for the first time by the car industry. And Toyota funded a project back in 2008, 2009. So 2006, we just been very successful with boosting and text on forests, and they were interested in the future of driving. And I remember having a very important meeting with the senior executive saying, do you really think in our lifetime we'll see autonomous cars? And I remember saying no. I really didn't think we'll see autonomous cars back in 2006, given the progress we were making in computer vision. But I did propose a big project where we would try and learn to recognize pedestrians and cars and roads to make cars safer. It was called, it was like an angel project. It was an assisted project that would just help the driver, never automate. So I think I was obviously misguided. Progress is so dramatic that we will see autonomous driving in our lifetime. But the idea then was taking neural networks. We knew that we could solve this problem very easily, that it shows an image and it can classify it as being whatever of a car. We looked at the problem slightly differently, in the sense we took the whole image and we tried to build some representation of its context, what objects are there, and then assign a particular class label to each one of those pixels. So this is semantic segmentation. Again, back in 2015, we built this very fast architecture with between 500,000 to 15 million parameters, different networks, that produced this pixel output. Now, to make it work, really was the hardest part was the data. We had to acquire these images of the road and label each pixel, and we paid students to do it, and nobody wanted to do this job. It took an hour per image, and we were paying $5. So it's a pretty awful task that nobody wanted to do. So you can see it's painstaking, it's difficult, you have to label. But that was the bottleneck. I remember when we did this database, we tried it on 700 images and we ran out of money, and we stopped at 700 images, and we divided it into a test set of 400, a test set of 300, and a training set of 400. So this is really small amounts of data. We labeled 700. We collected 21,000 images, but we only labeled 700 of them. And this data set really was so important for all our efforts in that followed on semantic segmentation. What was amazing, having trained only on 400 images, this segment algorithm, when we tested it on images it's never seen before in Japan, and in particular Belgium, the performance was noisy, but remarkably, this was a big surprise. So I remember having presented this to sponsors, and my preamble was, this method is not scalable because it's too expensive to label the images, but look, it works. And the car industry was so amazed by this that they said, well, if it works, we will pay people to label images. And then it wasn't hundreds of images, but millions of labeled images that were used to train the algorithms that are now running on autonomous vehicles. Back then, we weren't just interested in a neural network that produced an output. We were interested in some measure of uncertainty, and this is really holy grail. It's very hard to do this properly, but in those days there was a very simple trick which I rather liked, which is dropout. That is, you have your image, it goes through the network and it produces an output, one output. If you switch off some of the neurons, in particular at this bottleneck area, you get different outputs. And if you quantify the distribution of those outputs, both in terms of its mean and variance, you get a very approximate measure of model uncertainty, very approximate. But it was quite nice. It's very fast. It just effectively, you have 15 copies of the network, each with slightly different perturbed weights, and you get 15 answers, and you combine those to give you your mean and uncertainty. Right, and then this is obviously scaled to loads of these were these were the very early examples that we were testing in Japan, and uncertainty allowed us to pull out objects and images that we hadn't seen. For example, cones or different road architectures that we hadn't seen. Just the estimate of uncertainty on the right, whenever it's very bright, that was an image that it wasn't very good at, and hence that could be automatically pulled out and relabeled by hand. And these algorithms are, as everyone knows now, they're very, very efficient. They can run on mobile phones. We can do all sorts of semantic segmentation, different parts, different objects. Clothes in particular are a very surprisingly easy one. And again, back in 5 years ago, this was all running off mobile phones. So amazing hardware. The mobile phone now is as good as any hardware you get in terms of machine learning, both in quality of its cameras, RGB cameras, and in terms of the powerful processors that allow you to do run these in real time. Right, so that's the history lesson. Oh, blimey, we're not running out of time. Maybe I was a bit too slow. Let's go on to what is important. So what do we learn? Well, given networks and given enough data, labeled data, we know deep learning is great. However, getting this data is prohibitive in many, many applications. Also, the future isn't just heavily supervised. It's going to be all of these, in particular, multitask, multimodal. The most important thing is really getting more data using geometry, single images, and synthetic data. And more importantly, being able to self-supervise from video and in particular 3D. So that's really where we are. Now, I'm going to quickly go through some projects. Let me skip this because I think I've been too slow. So multimodal and multitask is obviously important. You don't train for a single task like segmentation. You train for many of these tasks, and you get better networks with better use of data. The second one I want to quickly talk about is camera localization, because I think this is the problem in the next couple of years will have enormous commercial impact. So the idea, can you take a picture and localize where it is in a city without using GPS? And we first started this project in 2002, where we built this data set of images and we registered them. And it's really a retrieval problem. You come back with a photograph, you try and match your database, the nearest neighbor in terms of its appearance, and then you know where that's taken from in blue, and you can calculate the new viewpoint. So the components are really images, retrieving the most likely image from a big data set, like so. This is sort of the task. Images at different time of day, different positions, and then finding point correspondences to actually verify the real camera pose. Now, this is a standard approach: image retrieval, and then very fine localization using point correspondences. Unfortunately, this is prohibitive in terms of the amount of data you need, and in terms of computation. Retrieving images is quite fast. Finding key features, matching key features, storing those key features is prohibitive. So we looked at the, very early on, we looked at the use of neural networks. Now, we know neural networks are great at finding parts of objects. We also looked at whether they could be used to regress camera pose. Now, where do you get your data from? This is the hardest thing. For each image, you need the three-dimensional position. For localization, it so happens that structure for motion gives us camera motion. That is, you can take a video, you can calculate the camera motion using this multi-view structure for motion, and you get for each image relative to starting point, camera position orientation. So this is more or less for free. You get the reconstruction and the camera motion for free. Hence, you can now train a network that can learn to produce estimate pose. Now, this was very early days, and I don't really want to say much about it. But in the next I would say in the next couple of years, this will be a commercially viable product, and it's a combination. At the moment, it's a combination of neural networks and geometry. Now, here's another example where we have just one image, and the task is the following. I want to be able to detect a meter and read the text. So this is a simple text recognition, and you can imagine it's straightforward. And finding a meter, I need to be able to detect it for different positions, orientations, and lighting. You would imagine you need a lot of data for that to do that reliably. And what we found was, I should explain commercially what are we trying to do. There are a lot of meters available in the world, and people want to read that data into their, for example, Apple Health without, and these might be old systems in hospitals or old devices in the home, which don't have Bluetooth or Wi-Fi. So they can't communicate directly to the mobile phone. There's a lot of this legacy equipment in factories and hospitals. So the idea is, can we use a mobile phone camera just to recognize and read the data directly into your Apple Health or whatever, into your app? That's what we're asked to do. Now, unfortunately, deep learning means we need hundreds of images of the object in different positions and backgrounds, and we need to recognize text. We need millions of different fonts and different text, so prohibitive to do, really. So we had a much simpler idea, which is we only need one image. That is, the user uploads a template of the object, and he specifies what the outline is. Remember, the outline of objects is going to be very, very important. Specifies what the outline is and where the screen is, and then he specifies some orientation of the screen. And then we build, we augment, so we're going to build a system that detects the screen, rectifies the screen, and reads the text. And it's all done completely with synthetic data. So just one image, we render all the viewpoints of the object on different backgrounds. And for the text, which is the hardest part, the biggest thing isn't the text, it's the reflection of the outside world. So this is hard, but we can synthesize all of that if we take arbitrary backgrounds and assume that the screen, in effect, can be reflecting anything in the world. So this is what makes it hard. So by doing this training data, this is all synthesized data, different fonts, different sizes. The key thing is synthesizing on loads of arbitrary backgrounds, because in the worst case, the screen is reflecting the world. And this is what the synthetic data looks like. You can synthesize these meters in different positions with different reflections. and you can train a very, very large, you can train. Now, the biggest problem is that the synthesized images here and the real images below, you can clearly see they're different. There's a big domain shift. And again, coming back with our sort of historical computer vision, that we know that most of the invariances, these look very different. But if we do, for example, edge detection, if all we care about is removing all those colors and intensities and just look at edges and outlines, in this converted representation, you get a very reduced domain shift. So by looking at things which you know are important, like outlines and edges, you really can ignore the artifacts from colors and lighting, and you get data which you can train from. And this was really solve a problem. So from one image, we can train any of these meter detectors. And the same with human body. This was the big surprise, the same technique. So again, the absence of real data and labeled data using things like edges. So this is what we did. These are real images. We have a proxy, which is really just very simple and cheap. We have edge detections, canny edge finding, and we have these joint detectors, which are, we know are, these are off the shelf. We know correspondence, deep learning for correspondence is a wonderful problem. Now, if we do this with our images, these are synthesized below, this is our real image. In this representation here, this proxy representation, there's a very small domain gap. You can see, although these images, the synthetic images look terrible compared to real images, in this pseudo representation, in this proxy representation, they're very close. You can't tell the difference between real and synthetic. And you can train, the silhouette's not as good, and dense object parts are not as good. So this is really important that we do this. And you can train a network to produce the edges and the key points. And then you can train a network to predict the SMPL or body parameters as distributions, not just their parameters, but their Gaussian distribution. So you get an estimate of body shape and uncertainty, and then you can repose these objects into the reference pose, and you can choose a network to fuse those. You can train a network which is going to use uncertainties to fuse them. And as I said, this is very fast. All it's taking your raw images, doing edge detection, key point detection, and estimating the most likely body shape. This is single view here, and then it's all merged to give you the most likely body shape in the last column. And all that's been done, the shape and pose is all done from synthetic data. Okay, the key point detection is deep learning, but standard off the shelf. Edge detection is your proxy representation. And then you've trained your network all on these synthetic examples, choosing arbitrary, exploring your body shape space and your pose shape with different backgrounds. And numerically, these are good results. This is a mobile phone app we're developing, where you can just point the phone at the user and try and estimate some of the important body shape parameters. For clothing, it's not precise enough for online clothing, but it is very precise for health. So being able to estimate body shape is a very big indicator of health in terms of visceral fat and fat and where the fat is distributed. So a very important health application. And then being able to do uncertainty means you can really represent when things are occluded. So this is the most important thing, that you get a bright red mean you don't really know. When object parts are occluded, you can represent that ambiguity and then use other sources of information to resolve the ambiguity. Okay, and that code is all available online, so please download it and play with it. So this is really exciting work. So I've been pretty quick, and I apologize for not being there in person, but I hope you're excited that computer vision is really amazing. This is the time to be a computer vision researcher. I mentioned these fundamentals of geometry, statistical modeling, and learning, and with examples of shape, pose, and shape, and recognition. All computer vision systems are a combination of the lot, and the big challenge for all of us now, this is present computer vision, not historical anymore. It's all about doing multimodal, multitask, being able to exploit very little data, and in particular synthetic data. Synthesizing has been one of the big tricks that have really, surprisingly, born fruit, especially if we're very clever in these proxy representations. So we can't really synthesize perfect photorealistic images, but we don't care. If you're learning to drive a car in a city, you don't care about each pixel being photorealistic. You care about the objects being in the right position and orientation. So things like edges and outlines are sufficient, as long as you get those correct, to be able to learn some of these things. Obviously, others are important, like traffic light color is very important. So synthesize is very important. And the big success will be in self-supervision with video. And finally, the real, as a field, we've come back, we can now go back to the real interesting problems. For a long time, I started in robotics, and it was impossible to do anything with robots because perception was inadequate. You had to have black objects on white backgrounds or white objects on black backgrounds to do any robotics experiments. Now we're at a stage where perception is quite mature and vision can provide this representation. We need systems that can learn not just from supervision, but embodied systems that are really moving and interacting with the world, even in simulation or with the real world. So learning from observations and interaction. Reinforcement learning is still not there for real robotic applications, but there are some interesting offline and model-based reinforcement learning, imitation learning that is relevant to real-time, real application robotics. And of course, with all these, people say it's impossible, explainable AI, we still need, and it's easily doable, to have a much better understanding of some of the limitations and how to interpret what the network's doing and transparency. So I'd like to thank all the students that I've been working with who've donated those slides, and I'm happy to take some questions. Thank you very much.
Thank you, Roberto. So any question in the audience? Yes.
Hello, can you hear me?
Yes, just. I can't see you, but I can hear you.
Great, great. Thank you very much for the talk that covers a lot of background. I wanted to
Yes.
ask about the work with the blood test.
Yes.
So it's interesting that we're now going back to finding the modality that bridges
Yes.
these different domains, like thinking is the same old style as finding these handcrafted features.
Exactly.
What do you think we need to do so that we can move beyond? I don't know, can we find these modalities automatically that can bridge domains?
Of course we can. It's just at the time, it's in these sort of applications we're very interested in. So you can learn that edges are important, right? That can be learned. We just know it. You know, it's the most obvious thing. If you want invariance to lighting, you
Right.
look at edges. It's the first lesson we did in computer vision 30 years ago. So we just hand coded that because it was the right thing to do. But is there a better thing that we can learn in terms of representation? Of course, we haven't done that, but so the system will learn the right representations. Ultimately, it's going to be something like boundaries and outlines and some other texture classifiers. But this is just a shortcut to avoid doing any of the learning. So it's a shortcut to do all the learning, but do all the learning with synthetic data. So I agree, it's not elegant. You should learn that modality, but but this is a simple solution. But good question, thank you.
Any other question? Yes, Gianluca.
Good morning, Gianluca Marcialis from University of Cagliari. I thank you for this very nice talk, this journey over your contribution on the state of the art. I would like to know your opinion about some characteristics of recent contributions, because I see that many of them strongly rely on the hardware technology available now. For example, deep learning would not be possible if we would not have, for example, the hardware of today. So I would like you to know your opinion about this correlation, this connection. Do you think that in the future this connection will increase, or there is still room to give some contribution independently of, in a certain sense, of the technology available? The second question is about the data. Today, you show us that the data availability is another, let's say, weak point for giving significant contributions to the state of the art. Do you think there is some possibilities to decrease this dependency on the data, especially when we have to apply some learning methods or something of the kind? Thank you very much.
Well, yeah, fantastic questions. That's a lovely question in terms of where we are in computer vision. In terms of the hardware, I think you're absolutely right. There's good and bad. The bad is you need a lot of data and a lot of special hardware to train some of these models. Now, in computer vision, a lot of I think the big ones are the language models, where you've got billions of parameters, and they're absolutely amazing, but very few people can train those sort of models. What I really hope is that once you've trained a perception model, for example, a key point detector for human body, or a semantic segmentation algorithm, well, if it's trained properly, and then that's available for everybody and can run on anybody's mobile phone or anybody's PC. So hopefully, if we can solve some of these core perception tasks, they will be just readily available code that people will use. They won't have to retrain a semantic segmenter, just as we hope they won't have to retrain. They can just fine tune a language, one of these enormous language models that can do their Q&A. So I think the hardware for training, in terms of data at the moment, it's the big companies, but I think those perception components will become readily available to all of us. In terms of the data, that's a really interesting one. The data, there's so much data out there in the world. So the trick is how we use data, in terms of how we get a supervision signal from that data. And I think if I think of the 4 decades, this next decade is all about self-supervision. So loads of data, which is very weakly labeled, but has some supervision signal, either from a different modality like audio or some other sensor, or things like video. But self-supervision is going to be the way we move beyond this paradigm of heavily supervised labeled data. So both good questions. So I can see hope for both of them. That is, we don't really need special hardware to run these networks. The mobile phones and those sort of processors are good enough for perception. But we might need very large resources to train some of these perception systems like language models. And then data's everywhere. The only thing that's difficult is labeling it, and that's going to be easier with some of the new technology and self-supervision. But good question.
Okay, thank you. We are very tight with the time. Thank you once
I apologize.
again.
Apologize for overrunning. I was a bit too slow, but thank you.
Thank you very much. Let's thank our invited speaker once again. Ciao, Roberto.
That's it.
So now it's time for the first oral session, Image Analysis, Detection and Recognition, chairing Professor Gianluca Foresti.
Okay, so good morning. So today I am going to present you the work entitled A Gain-Based Approach to Compare Identical Images with Generative Noise. This work has been done in the research department of the company Arianext, which is notably specialized in the analysis of identity documents. My presentation will be split into three parts. First, an introduction of the working context, then a presentation of the generic approach to compare images with generative noise, and finally, a conclusion about this work. In the past 5 years, gain-based approaches have shown impressive results in different domains. For instance, in image translation, a realistic photo can be converted into painting images, or the season can change from winter to summer, or the schema of a facade can be converted to a realistic facade. In image restoration, image can be colorized or can restore details that are hardly visible, which is really impressive. So now how these approaches can be used in the case of the analysis of an identity document. So we are dealing with the Romanian identity card, and more specifically with the problem of photo swap detection, which means to be able to check if someone has replaced the identity photo by checking the correspondence with the second photo that is called the ghost photo. This ghost photo is noisy. There are some text added on the photo and some wavelet pattern. So it's what we call a generative noise, a noise hiding in the generation process of the document. So to give an idea about the quality of those ghost images, we did a studies on 651 documents with two criteria. So first, if we look at the face, height, mouth, and nose, will we be able to recognize the person? If we look at the shape, we'll ask the same question, with obviously the limitation that two persons can have similar shape. And so we annotated three different criteria. Either the quality is height, medium, and low. So height, we can recognize the face, and low, it's almost impossible to recognize the face. And the conclusion of this study is that the data are difficult. More than 76% of the face has a low quality, and 50% for the shape. So in the second part, I will present the generic approach to compare images with generative noise, then I play into the case of the Romanian identity card, and finally present experiments and results. So as input, we have two images, an image without noise and an image with noise. And as output, we will have three different outputs. Either images are similar or different, or we cannot give an answer, typically when the quality of the image is too low. And to be able to return this output, we'll have four modules. We have an image with noise, so we will use gain algorithm to denoise the image. However, due to strong noise, it is not possible to reconstruct an image which is directly comparable to the first image. So we'll have a module that converts the image into comparable images. I will explain later in the case of Romanian identity card what type of images have been chosen. Then the system can give no response, so we have a module that's checking the quality. And finally, checking that the images are similar or not. So if we apply it to the case of the Romanian identity card, as input, we have the identity photo and the ghost photo that is converted, that is denoised with the GAN algorithm. Then they are converted into hash images. I will explain later how these hash images are generated. Then there is a step of quality verification, and finally, the comparison of images. So now if we look more in detail on how GAN approaches denoise the image. So we have two examples with, on the right, the ghost image, on the middle, the denoise image with the GAN, and on the left, the identity photo. So we can see that GAN is performing a good job to reconstruct the identity photo. However, we can see that some details are imprecise. So for instance, in example A, there is a beard that is reconstructed and it is not present in the original image. But if we look at carefully to the ghost photo, we can see that we can guess a beard. And similarly, in example B, the hairstyle is reconstructed is different from the original hairstyle, but effectively in the ghost image, we don't see this hairstyle. So what does the GAN is very coherent. He reconstructs from what he sees and he guesses when it is not visible. So based on this type of reconstruction, we can see that only the shape can be used to do the comparison. So we are building a simplification of this image that is called hash images. So instead of comparing the identity photo and the ghost photo, we will compare only two hash images. And those hash images are simply generated by using a K-mean algorithm applied to the gray level images with k equal 4. And the idea is to separate the background from the face, the hair, and the clothes. So it can happen that some hash images reconstructed have not a good quality, and there are three types of errors that we want to remove. The first, GAN can reconstruct a face which is not really good, and therefore the construction of the hash images is not good, so we want to remove this image. Similarly, when we have problem of elimination changes in changes hash images and it's not meaningful, so we don't want to use it. And the final problem, it can happen that sometimes we don't see any ghost image, any face in the ghost image, so it is an empty ghost, and still the GAN reconstruct a face, but we do not want to give an answer in this case. So to remove all of these cases, we are using some SVM classifier with OC features to detect those problems of quality. And finally, for the photo swap detector, we are building some dedicated features. So the first is the intersection over the union of darker and lighter pixels. The idea is in hash images, darker and lighter pixels are the most significant part of the image, so it's important to compare them. And then we are computing the proportion of pixels passed from the level I to G, and the idea is to quantize similarities and differences. So then we are learning a center and a covariance matrix and using a Madalobis distance with a confidence threshold to say that the images are similar and or different. For the experiment, so we have been using around 3,000 pair of identity photo ghost image for training the GAN, and in figure B and C, we have the train and test datasets. So now, if we are looking at the quantitative results, so we are comparing an identity photo with a ghost image. This is the input is A. The baseline is FaceNet that has been retrained on face from identity documents. And in the identity photo, we extract the face, we localize the face, we replicated this position in the ghost images, and we are comparing those two outputs. So it is the baseline in B. And then we compare with two approaches, so the baseline plus the reconstruction of the GAN instead of the ghost images, and the proposed approach with the hash images. So if we look at to work results, we can see the baseline does not work with 4% of true rejection rate from 1% of fast rejection rate. If we use instead of the ghost photo, the reconstruction of the GAN, we go to 11% of detection. And by using the hash approach, we are improving significantly to 32% of detection. And if we, in addition of the top of that, we are using the quality analyzer, we go to 52% of detection. So we detect more photo swap cases, but we don't give an answer in 22% of the cases. Now, if we look at more details to some error cases, so we have in A an example of false rejection, in B an example of false acceptance. As we can see, hash images are noisy. Two different people can be similar. And to take a decision, we have to fix a threshold to have a very low false recognition rate. So that's why it's explained that it is difficult to reach more than 52% of detection for this type of data. So as a conclusion, this work has presented a novel generic approach to compare images with generated noise. GAN algorithms are not able to reconstruct the original image due to strong noise and missing data. And the transformation into comparable images is therefore essential to deal with this type of noise. And this approach has been successfully applied to the Romaine identity card and shows significantly better results. Thank you for your attention.
Thank you very much also for the timing. Any questions? No question. I have one question about the comparison. You use the Malanobis distance and then use a local threshold to compare the image. Okay, you give it some more detail about this step.
In fact, I use a database to learn what is the best confidence threshold, and the results are shown on a different database to see how it works. So I've just learned this threshold on the database.
Okay, thank you. Any other questions? Okay, thank you very much for your presentation.
Thank you.
The second paper is titled Digital Line Segment Detection for Table Reconstruction in Document Analysis. The speaker is Puk Ngo. Thank you. 50 minutes for your presentation.
So good morning, everyone. My name is Puk Ngo. I'm going to talk about an algorithm for digital light segment detection for table reconstruction. I'm from Lorraine University in France. Let's first talk about the motivation of my work. So table detection is involved in image document analysis, and it consists in determining the okay, it doesn't work there. So it determines the zone in the image in which it contains tables. So in here, in the example, I highlight it with the green box, which is the bounding box of the table detection. Other tasks of document analysis contain the table structure recognition, which is high level from the table detection, which consists in determining the rows, the columns, as well as the cells in the table. So why the table detection? Because tables are usually used for summarized information in a structures and structural way, and it's present in many document images such as scientific paper, reports, and invoice, etc. So in this work, we are interested in the detection of table, in particular the materialized tables. The challenges of this task is on the variety of the layout and format of table in the document image. And also the task of table detection can be useful for to help for perform efficiently the recognition task and improve the data extraction from documents. So here is the content of the layout of my talk. So I will start with some background definitions and then the method for table extraction. And then I show some experimental results and conclude my talk. So the first definition is the definition of digital light. I forgot to mention that the proposed method is using the digital geometry tools for light detections. So the first notion I want to present is the digital light, which is defined by the set of points belonging to two parallel lines, in which the equation is given here. And there is particular case in which the we have AB is the direction of the line, mu is the shift, and finally omega for the thickness of the line. And when the thickness equal to the max absolute value of A and B, then we call it a knife line, which is a connected line. The second definition is the blur segment, which is based on the notion of digital lines. The difference is that in case of blur segment, you have a digital line that covers certain points, which is not necessary to be connected. And this is convenient for our framework of light detection for table detection, actually, because the light could be interrupted or damaged due to the acquisition process. So here is an example of the blur segment that you can see the points not connected. The third segment, the third definition is the directional scan. That is the definition that which is another partition restrict to a grid G of a vertical ID into the segment of nice straight line that I presented previously. So in order to illustrate, so the equation is given on the slide. So in order to illustrate this definition, so let's try to build the directional scan that based on the 2 point P1 and P2. So the first part is the straight line D, which pass by, that is defined by the 2 point P1 and P2, from which we define the first knife straight line and 0, and then we start on the left and on the right side of this knife segment that will give us the directional scan. The final definition is the adaptive directional scan, which is a dynamic version of the previous definition, in which we can see that there is an online registration of the knife lines according to the curve instead of static at previous one. So here's now the framework for table extraction. So our framework is based on the flash blur segment detectors, that is called as BSD. This is a digital geometry tool. It's used for detect segment in the image. It's contained of 4 steps, and as an input, we give a 2 point A and B that's passed by the segment. So the first step of the method at VSD is to find a blur segment B from the Haggard gradient magnitude pixels using the directional scan that I presented previously. And then some test of line and sparsity is performed to decide if the detection could be pursued. And then the second step of the third step, which is the main second step of the method, is the file tracking that build a final segment B prime from the local gradient maximum using the adaptive directional scan in order to extend the blur segment B prime in an appropriate direction. And finally, some test of length and sparsity of B prime is performed to output the finally B prime. So from the basic FBSD detectors, by using the prominent local maximum of gradient A and B, a multi-detection can be performed in order to detect all the edge that's crossed by the 2 point A and B, in which a occupancy mask is used to avoid multiple detection of the same edge. And an extension of this method for multi-detection for a full automatic detection is performed by using a light segment that's crossing the whole image and is swept by vertical and horizontal direction in order to detect all the segment on the blur segment on the image using the multi-detection. And of course, a validity test is performed to reject all small segments. So, so here is some precision for the table extraction framework. So in this work, we are interested in materialized tables. So those are tables with rectangular form and could not be closed. So example here, but it must compose at least the line segment, intersecting at right angles. And it must contain at least 2 surrounded horizontal lines that is bounded of the table and at least 1 inside vertical line to define the table. So on the first line in the 4 figures, the first figure on the 2 figure on the first line is the materialized tables. On the other side, the other 2 on the second row is not materialized table by definition. Okay, sorry for, oh no. sound to have some technical problem.
There is a system problem with the file.
The file is failed.
Non può usare il suo computer? Siamo collegati in rete con NDI, non può usare il suo computer.
Okay. Insert your USB pen again. You need okay. Okay, apologize for this inconvenience. We move to the next paper, and then we come back after we have solved the problem. Next paper is accelerating video object detection by exploiting prior object location. The author and speaker is Berker Ulker. Thank you.
Hello everyone, this is Berk Ülker from Eindhoven University of Technology. Today I will present you our work on accelerating video object detection by exploiting prior object locations. Our goal was to improve the efficiency of the object detection for the video object detection tasks, and to do this we basically aim to accelerate the object detection. And as a case study, we picked single-shot object detectors because of their efficiency. And we provided a set of generic modifications on the single-shot object detectors. These are exploiting prior object detections, prior object locations coming from other modules in the pipeline to focus computational resources. And second, the generation of a set of crops based on this prior information, and then finally use of smaller input resolutions for detection on the crop patches to accelerate the detection. Overall, our method can achieve the state-of-the-art accuracy while improving the execution time. And we executed our experiments in two public data sets. One is UAD track and the other one is the UAVDT. And maximum speed of 1.7 on UAD track and 1.6 on the UAVDT has been achieved. So back to our motivation, the scene monitoring for the traffic monitoring tasks have additional challenges in object detection. And one of them is the real-time processing requirements that has to be often executed on this deployment field. And also the resource-limited environment. And we aim to tackle these challenges by accelerating the object detection task. So our contributions can be summarized in two main items. We accelerate the object detection by exploiting the scene sparsity, and then modification of the object detector architecture to use smaller input resolutions. And second one is our empirical evaluation of the algorithm on two real-world data sets. So to summarize our proposed methods, we have two key improvements on the single-shot object detectors. We first modify the detector to work in a crop-based manner and then exploit the scene sparsity, and then use small input resolutions and modify the detector head accordingly and train the network accordingly to increase the execution efficiency of the object detector. So this is the overall pipeline of our method alongside the original baseline method. So compared to the baseline, we first start out with input frame plus prior locations, and then generate some crop regions around the objects of interest, and then pre-process and execute object detection on these crop patches. In the first stage, we basically generate these crop regions based on the prior information, and here we basically want to find a good trade-off between speed and accuracy. And to do that, we first limit the redundant area and then ensure that every object in the scene has been covered. In the meantime, we also consider limiting the resize factor, because when we are processing these crops, the crops will be resized accordingly to the input resolution size. And we have a three-step procedure to execute this. First, we expand the prior locations in order to ensure the object coverage. And then we check possible merge operations controlled by the merge size threshold parameter. And then we traverse possible merges and generate crops. In the second stage, we use a modified SSD architecture. Instead of using the original SSD architecture, we decide to use the SSD-ML, which is basically an addition of the objectness score on the original architecture. The backbone network for the feature extraction is the same, VGG16, and the detector is trained for multiple input resolutions. For each resolution, we used equally spaced object prior size in the detector head. And for the inference and post-processing, we have some additional steps. In the inference, we basically introduce the batch inference for multiple crops for efficiency. And the inference also includes the crop region calculation for each frame. For the post-processing, we have an additional merging step. And here we, instead of using non-maximum suppression, the original one, we decided to use class-agnostic NMS using the objectness scores. Training procedure for the crop-based approach is a little bit different than the regular training of the SSD. Here we have some additional modifications to address the challenges that we see in the training. In both datasets, we've seen that the class distribution of the objects is not really fair, and we decided that with some bias on underrepresented classes, we can improve the overall accuracy. And then we define a random box around an object, and then basically create a crop around the random object to generate a training batch. In the same way, we execute this over multiple images and form training batches. In our experiments, we use the evaluation metric of mean average precision from MS COCO, and we use two different platforms. First one is a rather powerful GPU, GTX Titan, and the second one is an embedded platform, TX2. We changed the inference crop size and the training crop size parameters, and then used three different resolutions in the evaluation. Here you see the results of our method compared with the baseline. On top you will see the baseline, and in the following three rows you will see the results from our networks matching the accuracy of the baseline. You can see that the execution time is significantly improved while delivering more or less same average precision. And on the following three rows you will see that the performance increase, the accuracy increase, while matching the execution time on the Titan X. Here's the speed accuracy trade-off that we achieved in the D-track. You can see here several curves for different resolutions, and the baseline network is represented by a green dot. For each dot in these curves, we have a different crop size. As you can see on this data set, the clear winner is the 64 by 64 network, defining most Pareto optimal points. The same experiment is executed also in UAV-DT, and you can see that we still have some more Pareto optimal points, but from multiple detectors. This is mainly caused by the object size distribution of the UAV-DT compared to the D-track dataset. Since this dataset is recorded using a UAV from a different viewpoint, there are also really small objects that cannot be recognized by a larger network due to the resize factor. So here is a snapshot of our cross-section of our results from the network by 64 by 64. We basically made a scan of crop size parameters for the inference and the training. Here you can see that if both parameters are matching, basically if you train on and execute the inference on the same crop size, you will have the best performance. And to conclude, we presented a novel crop-based object detection method for use in video-based systems for roadside and drone-based traffic surveillance. And compared to the baseline, we achieved several Pareto efficient operating points. And our method achieved up to 1.7 speed up on UAD track dataset. And accuracy is improved with 11% at 1.1x speed for the same dataset. And for UAVDT, these results are slightly different, but we again achieved our goal of increasing the execution efficiency on the same accuracy. So this is the end of my presentation. I would be happy to answer your questions.
Thank you very much. Questions? Some questions? No question. I have a very short question about in the cropped images. What happens if there are shadows, or, for example, partial occlusion in the object for the detection?
Shadows and the partial occlusions.
Yeah.
The partial occlusions are actually not handled separately. This is the same way that the baseline, which is using the full image, is handling the occlusions. So if you are executing the detection on every single frame.
Like for the dimension of the bounding box.
The bounding box, dimension of the bounding box is determined by the expected size and the location of object coming from the prior information. So the upper bound of the accuracy of our method is basically limited by the accuracy of these prior locations as well. But in this study, we didn't discuss or go into the details of these prior locations. So we assume that they are available from the other modules like tracker or motion detector.
Okay, thank you. Any other questions? No, okay. Oh, one question.
Thank you for the presentation. Have you made some evaluation or assessment about your approach and the traditional ones? Because you are adding another layer of cropping. And have you any indicator about the latency of your processing in comparison with the others?
By the others, you mean the baseline probably, or the original full scale image detection? Yeah, you actually see here the green dot in this slide. You no longer see that. Okay, so we took the baseline as the original SSD, which is using 512 by 512 image as an input. So this is more or less similar to the baseline SSD network. So we are just showing that our method, our modifications can improve a single shot object detector in this way. So for the other works that are similarly handling this problem, it's mostly targeting the accuracy rather than the execution time. So you can see that they improve the accuracy significantly, but they are using significantly more computational resources.
Okay, thank you very much. No other questions, so we can move to the last presentation of this session. It's a remote presentation. The title of the paper is Learning Semantic for Visual Place Recognition Through Multiscale Attention. The speaker is Antonio Tavera. I don't know if the speaker is online, is ready.
Can you hear me?
Okay.
Good morning, everyone.
Good morning, please.
Okay, so my name is Antonio Tavera, and I am one of the author of this paper that is entitled Learning Semantic for Visual Place Recognition Through Multiscale Attention. In this paper, we address the task of visual place recognition And we present the first algorithm that learns robust global embeddings from visual appearance and from the semantic content of data. We access the validity of our method on several datasets, and we present also our novel synthetic datasets suited for both the place recognition and the segmentation task. Let's start from the task. Visual place recognition is the task of recognizing the location where a photo was taken. The common approach is to usually cast this problem as an image retrieval problem, where the location of a photo, to which we refer as query, is estimated by comparing it to a huge database of geotagged images, to which we refer as gallery. And despite the advancement made possible by the usage of deep convolutional neural networks, the existing visual place recognition techniques that construct global descriptor by extracting appearance features and then aggregating them do not generalize well across different locations and scenarios. Neither, even if the knowledge is increased through the attention process. And recent research has discovered that these issues may be addressed by developing image descriptors that are based not just on visual appearance, but also on the semantic content of data. The main contribution of our paper are twofold, starting from the intuition that not all the semantic content is useful for the visual place recognition task. We present a novel method to generate highly informative global descriptors, letting the visual place recognition task guide the segmentation model via an attention mechanism. And we also present a novel synthetic dataset for large-scale visual place recognition that also contains pixel-wise labels. I start presenting our synthetic dataset. That is the second release of the well-known IDA dataset. It contains more than 40,000 images that are captured across 2 different cities with GPS information and the pixel-wise annotation for 25 semantic classes. This dataset is from today available to download at the link here. Our proposed architecture consists of a single encoder shared by 2 different tasks, the visual place recognition task that is shown in blue lines, and the semantic segmentation task that is shown in purple lines. By sharing the same encoder, the 2 tasks induce it to learn features that combine both the visual information used for the visual place recognition task and the semantic information present in the scene. However, without a proper mechanism to control this fusion, the model would equally focus on all the semantic classes, regardless of their actual relevance for the visual place recognition task. We introduce such a mechanism in the form of a multi-scale attention module that is trained only on the visual place recognition task. But this module, it also modulates the features extracted by the semantic segmentation decoder. In this way, the visual place recognition guides the semantic segmentation task, informing where to focus on the scene. In our architecture, the multi-scale attention module becomes instrumental to make the place recognition guide the semantic segmentation model during training. It leverages the encoder output features at multiple spatial scales to capture objects with different sizes, and it produces final output a map M that marks the retrieval salient region. The scores that are in the attention map indicates where the retrieval is focusing. In visual place recognition, it is widely common to use pooling layers to extract compact global descriptors for the retrieval process. In order to exploit the semantic and the appearance information at a different abstraction level, we introduce a multi-scale pooling layer that uses features extracted at different levels of the shared encoder. We use the weakly supervised triplet margin loss to train the model to extract descriptors for the visual place recognition task. For each training query, we consider a positive and a negative example drawn from the gallery. The positive example is an image of the same place as the one depicted in the query, where the negative example is an image of a different location. Both the query and its corresponding positive and negative examples are from the source domain. Therefore, we can use the available GPS information to select the examples. The semantic segmentation task informs the feature extraction process with semantic information. And for this purpose, we use a semantic segmentation decoder. However, to force the model to focus on semantic information that is most discriminative for the place recognition task, the output of the decoder is weighted by the attention map M, which is trained by the visual place recognition task alone. To train this shared encoder and the decoder, the semantic segmentation branch uses a standard cross-entropy loss. The new synthetic dataset provides the training data, but there is a significant gap between the images from the simulator and the images from the real-world scenario, like the Oxford robot car dataset that we used in our experiments. And to reduce this gap, we use an adversarial training that aims at aligning the features extracted from the synthetic domain to the target one. The overall training loss function becomes the one that you are seeing here at the bottom. We access the effectiveness of our approach, comparing it to GEM and RMAC, that are two state-of-the-art visual place recognition methods that use global descriptors. We also compare to DESGIL, which similarly to our method uses semantic information, but it selects them in a top-down manner. For the evaluation, we use the Oxford robot car dataset, which is a collection of images from the city of Oxford taken into different environmental conditions. We use the overcast scenario as the gallery, while the queries are divided into 4 scenarios that are the rain, the snow, the sun, and night. From these experiments, we observed that all methods perform worse when tested on queries from the night and sun scenarios due to a stronger visual dissimilarity with respect to the gallery images that are taken from an overcast scenario. But overall, we see that our architecture outperforms all the other methods with and without domain adaptation, from a minimum of 8% to a maximum of 24%. And we further confirm the potentiality of our method, testing the generalization capability on very large city datasets. And these results demonstrate that our solution is able also to generalize to unseen domains better than all the other methods by usually a large margin. The qualitative results that are present in the main paper, but you can find a lot of them in the supplementary material, confirms the assumption that by conditioning the semantic segmentation on the place recognition task, our model is able to draw information only from these semantic categories that are most discriminative for the place, thereby outperforming the current state of the art on all the tested scenarios. Concluding, I have presented a new method for generating global descriptor for visual place recognition that exploits both the visual appearance and the semantic features at different scales. Our solution let the model to determine what semantic information to use in an adaptively way. And moreover, we contribute with a new dataset that is rich of RGB images under different environmental conditions, pixel-wise semantic mask, and obviously GPS coordinate. This, we believe, will be very useful to the entire research community. Here you can find the references, but I can share with you the set of slides if necessary. And If you follow this QR code, you can also find the code and the link to download the dataset. Thank you for your attention.
Thank you, Antonio. Some questions from the audience? No questions. So, Antonio, I have just a question about the F function in slide 7, I remember. You have a couple of local F functions. We are concatenated to obtain the global one. Can you give some detail about this concatenation operation?
Okay, the F function is just are just the features that are extracted from the shard encoder network. We select just the last and the second last set of features, and then we pass them through 3 different convolutional layers and just concatenate them in a simple and general way.
Okay.
And then to a last one per one filter to produce the final attention map.
Sure, okay.
But they are just the last features and the second last feature of the shard encoder.
Okay, very clear. Thank you. Thank you.
You're welcome.
Any other questions? No? Okay, thank you very much, Antonio, for your presentation. Now we come back to the second one in order to conclude the second presentation.
Okay. Sorry for the technical problem, and I hope you still remember what I told previously. So here's the framework of table extraction is based on 5 different steps. The first one is using this input image that you see here on the slide. We will first, the first step will be using the FBSD, the light detectors, to detect all the lights on the image. This light can belong to the tables as well as graphic image on other kinds of point that belong to, could be lines. And the second step is once we have the different kinds of segment, we will try to extract only horizontal and vertical segments that for us belong to the tables. And due to the impact of scanning procedure, we accept some tolerance of angles of 5 degrees. The third step is because sometimes the light can be broken due to the acquisition noise and degraded conditions, so we will try to prolongate the segment and connect the vertical and horizontal segment that we detect previously, and then we create the long segment, as we can see here on the figures. Well, we cannot zoom on the figure, but still we can see some segment that belong to the text here in the red, and some belong to the graphic, etc. The fourth step is related to remove on the segment that not belong to the table, so in particular those that belong to the text. So for doing that, we will use some local analysis of gray intensity profile, so that we can observe if the segment detected, the vertical or horizontal segment detected belong to a table, then the profile will have this kind of form. Otherwise, this will have a variance in intensity during along the lines. So using this simple analysis, we can remove the segment belonging to the text. And the last step would be related to reconstruct the table cells and then combine all the connected components of the table cell to have the table, as we can see on the figures that we obtained. So that is the proposed method. So now I will move on the experimental results. In order to evaluate our method, we will use the 3 publicly available datasets, which is on the slide, and for the evaluation measure, we will use some standard ones, so recurrent precision and F measures, with the pixel from the ground truth and the one from the method. So in order to compare the proposed method with the literature's method, so we choose 4 different one that in on the slide. So the first one is a method based on the component of the layout analysis module. The second one is based on random transform. And the last one is a deep learning method. So this table shows the result on the different measures that I mentioned previously on the 3 data sets. So as we can see, the proposed method not always give the best result, but it's quite competitive result and well score comparing to the other one. And it's not, yes. The last thing I would want to say is the limited case that would fail in the proposed method, which is related to the non-materialized tables that we can see here on the example, the table without borders. This is not have vertical lines inside, or sometimes it could relate to graphic, matrix, or image on the image, on the document image. So now time to conclude. So in the present paper, we have proposed a method for table extraction from document images using discrete geometry and classical image processing methods. And the experimental results show a competitive to the existing methods. In perspective, we would like to apply our method for table structure recognition with related to extract information in the cells and column or rows. Other extension could be in consideration is for non-materialized tables in which we have to find out another strategy instead of based on only on the lines, and further to conduct more experiments. So thank you for your attention, and again, sorry for the time. More detail can be found on the paper, of course, with the more detailed technique on the main paper, and here are some references in case you want to have a look on the different methods. Thanks again for listening.
Thank you for the presentation. Very short questions. Any question? I have just a very brief question about the comparison. So have you compared your approach with classical approach like half transform or template matching, something like that?
Actually, the second method is based on random transform, which is also very similar to Hertz transform. And I didn't compare to the template matching.
Okay, thank you. Any other questions? No, okay. Now we conclude here this first oral session of the conference. We move to the coffee break. And I remember that it is forbidden to come back in this area with coffee, food, and something like that. Thank you for the patience. Okay, thank you.